Today, we're gonna unlock one of the coolest ideas in physics, a kind of hidden energy that explains everything from why your kettle works the way it does to how our own bodies cool down. You know the feeling, right? You're exercising, you start sweating, and almost right away, you feel cooler. But why? How does that simple bit of evaporation have such a massive cooling effect on your skin? And hey, here's another one. You can have a pot of water boiling away on the stove and crank the heat all you want, but a thermometer in that water will just stubbornly sit at 100 degrees Celsius. So where is all that extra heat actually going? Well, get this. The answer to both of those puzzles is the exact same thing. So here's our game plan. We'll start with that everyday heat mystery, introduce this idea of hidden heat, and figure out why the temperature stays flat. Then we'll see latent heat in action, go over some common traps you need to avoid, and then wrap it all up with the key takeaways. Right, so where is that energy disappearing to? Well, the answer lies in this fantastic concept called specific latent heat. It's the absolute key to understanding what happens to energy when a substance changes from one state to another. And really, the biggest clue is right there in the name. The word latent literally means hidden, and that is the perfect way to think about it. This is the energy that's doing all the hard work behind the scenes. Okay, so here it is, the official definition. Specific latent heat is the energy you need to change the state of 1 kilogram of a substance. We're talking melting, boiling, that kind of thing, but, and this is the absolute crucial part, without changing its temperature at all. That's the mind-bending bit. Now, this hidden energy comes in two main flavors. You've got the latent heat of fusion, which is for solid to liquid changes, like ice turning into water. And then you have the latent heat of vaporization for liquid to gas changes, like water turning into steam. And it works both ways when things cool down too. And you're gonna love this. The formula that ties it all together is beautifully simple. Energy equals mass times specific latent heat. E equals ml. That's it. This little equation is your most essential tool for any of these calculations. Okay, but here's the deal. To make this formula work, you have to get the units right. Energy, that's E, is in joules. The specific latent heat, L, is in joules per kilogram. And that means, and this is where so many people trip up, the mass M must be in kilograms. Forgetting to convert from grams is probably the #1 mistake people make. So we know the temperature stays constant during a state change, but why does that happen? I mean, really, what's going on? To figure that out, we need to zoom all the way in and look at what the individual particles are actually doing. Here's the story. You add energy to the substance, but instead of making the particles move faster, which would raise their kinetic energy and therefore the temperature, that energy gets a totally different job. Its mission is to weaken and break the bonds that hold all the particles together. So since the particles aren't actually speeding up, their average kinetic energy doesn't change. And because temperature is just a measure of that kinetic energy, the thermometer reading stays completely flat. Okay, that's the theory. But the best way to really wrap your head around this is to roll up our sleeves and put that E equals MC formula to work. Let's do a couple of quick examples. All right, problem number 1. How much energy do we need to completely melt 0.2 kilograms of ice? We're also told that the specific latent heat of fusion for ice is a pretty hefty 334,000 joules per kilogram. This is nice and straightforward. We start with our formula, E equals M times L. Then we just plug in the numbers we have. So E equals 0.2 for the mass, multiplied by 334,000 for the latent heat. Now we just calculate. And we get 66,800 joules. Now just stop and think about that for a second. That's a huge amount of hidden energy required just to turn ice at 0 degrees into water that's still at 0 degrees. Wild, isn't it? Okay, let's flip the problem around. This time we know the energy. Let's say a kettle supplies a massive 840,000 joules of energy. We're given the latent heat of vaporization for water, so the question is, how much water can all that energy actually turn into steam? For this one, we just need to do a quick little shuffle of our formula. If E equals M times L, then mass, M, has to equal energy divided by L. So we just substitute our values in. That's 840,000 joules divided by a whopping 2.26 million joules per kilogram. And the answer is about 0.37 kilograms. So all that huge amount of energy from the kettle boiled away just 370 grams of water.
That's barely more than a can of soda. It just shows you how much energy it takes to vaporize a liquid. Okay, now for a really crucial part. Let's talk about the common mistakes that trip people up again and again. Seriously, knowing what to avoid here is going to give you a massive advantage. So let's just run through these classic errors so you know exactly what to look out for when you're tackling these problems.
First, that unit error I mentioned. Always convert grams to kilograms. Second, remember the core idea. The temperature does not rise during a state change. Third, make sure you're using the right L value. Is it for fusion or for vaporization? They are very different. Also, don't confuse latent heat with specific heat capacity. That's about changing temperature, not changing state. And finally, remember, energy is absorbed to melt or boil, but it's released when you freeze or condense. All right, we've covered a fair bit of ground, so let's boil it all down to the absolute essentials you have to remember. Here we go. 1. Latent heat is the hidden energy used for changing state, not for changing temperature. 2. Your formula is E equals mL. 3. Fusion is for solid liquid. Vaporization is for liquid gas. 4. Temperature stays flat because you're changing the particle's potential energy, not their kinetic energy. And 5. It almost always takes way more energy to vaporize something than it does to melt it, so LV is usually much bigger than LF.
And I'll leave you with one final thought to tie all this together. Both steam and boiling water are at 100 degrees Celsius, so why is a burn from steam so much more dangerous and severe? The answer is all about that hidden latent heat we've just been talking about.